Stoichiometry. This is probably my favorite unit in chemistry because I think it's a lot of fun. There is a very specific routine that comes in with stoichiometry, and as soon as you get that routine down, it's going to be pretty straightforward getting through this. Because I like stoichiometry so much, I often refer to it by a term of endearment, which is stoichy. This is probably what you'll hear me call it throughout this video. So we know that we use molar conversions to compare units within the same substance. And we have our nice friendly mole city map to help us do that. Mole city map contains mole city in the center and the three suburbs around it, which are Masstown, Volumeburg, and Particleville. However, the drawback is that mole city only allows us to use molar conversions between one substance. In order to compare units of different substances, we use stoichiometry. And the great thing about this is that we can expand our mole city map into the map of the stoichiolinus. And this helps guide us through stoichiometry. So if we're looking at the mole city map we've already drawn as South Stoicholina, all we have to do is create another mole city map for North Stoicholina. This will be the second substance we are comparing. This mole city map is set up exactly the same way as our original mole city map. We have mole city, Particleville, Volumeburg, and Masstown. Now, if you notice, there aren't any obvious ways to travel between South Stoicholina and North Stoicholina. Because infrastructure wasn't very well thought up here, we only have one way to do this. And that is by using a railroad known as the mole city or the mole ratio line. Our mole ratio line is the railway to get us between South Stoicholina, or substance 1, and North Stoicholina, which is substance 2. The mole ratio is a comparison of the moles of two different substances. The best way to explain this is to look at how it falls out in an example. So pause the video here and finish writing down whatever you need from this page before we go on. All right, our first example. Using the Stoicholina's map, we can really convert between any two units. In this example, we're going to be looking at mass just because it's nice and simple. Since we're looking at mass the whole time, we know we're going to be starting with Masstown of South Stoichiometry. South Stoichiometry, remember, means substance 1. We cannot go directly from Masstown to Masstown. Instead, we have to first go from Masstown of South Stoichiometry to Mole City of South Stoichiometry. So for both of these, we are still in South Stoichiometry. After we get to the mole city of South Stoichiometry, we can use our mole ratio in order to get to mole city of North Stoichiometry. Remember, North Stoichiometry just means substance 2. We don't want to end up in the moles of our second substance. Instead, we want to get to Masstown. So we are going to continue over from Mole City of North Stoichiometry to Masstown of North Stoichiometry. And we're going to use our very familiar molar mass road to do that. The most important step of stoichiometry is starting with Swabe. Swabe is starting with a balanced equation. Yes, it's another one of Dr. Dom's terms. So go ahead and look at our example problem here. Calculate the amount of grams of ammonia gas produced by the reaction of 5.40 grams of hydrogen gas with excess nitrogen gas. Using that information, you'll be able to create and balance the equation. Pause the video and do so. This is what I got. N2 plus 3H2 generates 2NH3. It is critical to start with a balanced equation here because our mole ratio comes from our coefficients. Looking at our coefficients, we have 1, 3, 2. These coefficients make up our mole ratio. Our mole ratio will be 1 to 3 to 2. The next thing we need to do is identify what we're looking for. We are looking for grams of ammonia gas. To find this, they have given us 5.40 grams of hydrogen gas. This is our known value, and that's what we will start our conversion factors or conversion tables with. Now, if you notice, we've already mapped out what we're going to do, so we can count how many conversion factors we'll have. Here, we'll have 1, which is molar mass road. Here we'll have a second, which is our mole ratio line. And here's a third, where we will have molar mass road again. because we know what steps we're going to do or which conversions we're going to use, we are going to go ahead and set it up with our units and our substance before we start adding in our numbers. Our first factor is right here, going from mass town of substance 1 to mole city. We want to cross out our grams of hydrogen gas, so we will put this on the bottom. Our molar mass is grams per mole, so moles of hydrogen gas will go on the top. That delivers us here to our mole city of South Stoichiometry. We will then use our mole ratio line to compare moles of substance 1, hydrogen gas, to moles of substance 2. This is ammonia gas. Again, we're going to cancel out moles of hydrogen gas, so we put it on the bottom. On the top is where we'll put our new substance, moles of ammonia gas. Now that we are here in mole city of North Stoichiometry, or substance 2, we are going to use molar mass to convert to mass town of substance 2. Wanting to cancel out moles of ammonia, we put that on the bottom. And our grams of ammonia will go on top. At this point, we can actually go through and cross everything out to make sure we're ending in grams of ammonium gas. These two cancel. The moles of hydrogen cancel. The moles of ammonia cancel. And we're left with grams of nitrogen, or grams of ammonia gas. Exactly what we want. Now we're going to add our numbers. We know, or we can calculate, that the molar mass of hydrogen gas is going to be 2.016. And we know that this is per 1 mole because it's a ratio. Here, when we're looking at our mole ratio, we need to come back over to our balanced equation. Identify hydrogen gas. It has 3 moles. So we're going to put 3 here. Finding ammonium gas, it has 2 moles. So we put the number 2 up there to show our 3:2 ratio of hydrogen gas to ammonium gas. Then we come over here to finish out our numbers. We know we have 1 mole because of the mole ratio. Because of our molar mass ratio. And on the top, we use the molar mass of ammonia, which is 17.034. Now we're at the point where we're going to do our math. 5.4 divided by 2.016, because remember, 1 doesn't really do anything. Then we have to multiply by 2/3. This is a fraction, so we have to multiply it like this. After we've done that, we are again going to multiply by 17.034 because dividing by 1 doesn't do anything. This will give us the answer of 30.418. Grams of ammonia. Remember, we have our numerical answer, our units, and our substance. To summarize, I have listed out our steps again. First, we swab A. Then we identify what we want to know. We begin the conversion with our given amount, set up the conversion factors or tables, and then we do our math. This is very similar to molar conversions.